Okay, so as the name suggests, it is not going to be inverting, which is V out to V in will not be negative. Okay, but we'll see it will be clear once I do the derivation. Okay, so the circuit for the non-inverting amplifier is something like this. Okay, so what has changed? You see that there's very minimal changes from a inverting amplifier. You can quickly look at the inverting amplifier. So that's the inverting amplifier. And this is the non-inverting amplifier. Inverting, non-inverting. You see the difference? Just that the voltage source has been moved. So the voltage source here is on the negative or the inverting end of the amplifier. This is for the inverting amplifier. Here the voltage input is the positive one or non-inverting input. That's all. You'll see that the equations are much different for this. Okay, so let's try to compute the ratio of V out to V in. Yes, for that. And so this is sort of a reinforcement on what I did earlier. So it's going to be essentially the same process. Let's first assume various things like we did for circuits, essentially the currents. So say that the current here is I used I in earlier because there was a voltage source here, but let's just stick to the same one. You could assume whatever you want, I in. Okay. The current flowing through the output is I out, so that will go in like this. Okay, then there'll be I negative, I positive. We know that those two are 0. We also would have a V positive, V negative. I'll just write it down there. V negative, V positive. Okay, I think that's pretty much it. Once you have this, we already tried equations. Now, what we're trying to do here is we're trying to write an expression for the ratio of V out to V in. Okay? And like the previous case, I think it's advantageous to try to figure out what is the voltage at this point. Let's call that C. Okay, so you want to find the voltage at C. If you get the voltage at C, just makes our life easy to write the equations for the op-amp. Okay, so what sort of equations we have? We have see V out. So V out is the voltage here minus VC, voltage there. So VC is the voltage here, V out is the voltage there. That's because there's no resistor between this point and that point. You can just write it as VC. So V out minus VC should be equal to the potential drop across the resistor RF. So I out RF. So I have one equation for V out. We try to get the other equation. So we can see that V in is connected to V positive, right? So clearly V in should be V positive, because that's connected to the positive or the non-inverting end of the op-amp. But we know that from the assumptions we have for an ideal op-amp, V plus is the same as V minus. Op-amp assumption. Okay, and then we can also see that since C is connected to the negative end of the op-amp or the non-inverting or the inverting end, we see that VC is the same as V negative, right? Just from here, C is same as V negative. Okay, so from these three things, VC is V minus, V plus is V minus, we can see that V in is nothing but VC, right? Yeah, but an error here. This should be V plus. V in is connected to V plus. Okay, so from all these three things, you can see that V in is VC. Okay, so what I'll do is I'll rewrite this equation. This equation. So let me just copy paste this again. This makes it easy to refer to that. Maybe I should just change it. So what we'll do is we will use this expression and this expression and V out minus V in is I out RF. Okay. Okay, so let me now copy this. This is from previous. Okay, now I do have V out, V in, but I don't like the I out there. I need to eliminate I out. So what I'm going to do is I'm going to see if I can relate I out to perhaps I in. So you can see that at C, we can sum the currents going into C. So we have I out is going inside C. I in is also going inside C. But what is coming out is I negative. But our assumption is that the current going through the op-amp is 0, and that's because the output impedance is very high, right? This is op-amp assumption. Okay, so we have now another formula for, we have a formula for I out, which is negative I in. But that doesn't solve our problem because now we have substitute one unknown with another unknown. So we need to find an expression for I in, right? So let's do that. So we see that there's I in here. Perhaps we can relate I in with something with the resistance. So why don't we compute the voltage drop across the resistor R? So we know that VC is the potential on the right. 0 is the potential for the ground. So VC minus 0 is equal to I in times R. Now, there's one catch though. I did not put the current direction is this way, right? Because then I said I out plus I in. So currents going through C should equal to I minus. So I assume that the direction of the current is this way. Now, we know that positive current is when it flows from positive end of the battery to the negative end of the battery. So when we have plus, this is how we show the current, right? Let me show a resistor. So always goes from positive to negative. But here, our assumption is that the current is flowing from 0 to C. So that's like the opposite direction which you would assume the current to flow, which means that I need to take that into account. That is, since C is at a higher potential than 0, and my direction of the current is not the usual convention, it is not from positive to negative, I need to put a negative sign here. This is because ion is assumed to flow from 0 to C or 0 to VC. Okay, now you could have obviously changed the direction of ion, which means that this will change, and that will also be fine. We'll get the right answer. Okay, so now I think I have about everything I need to solve this, but let me just sub in the value for VC. What is VC? I solved for VC in the previous page. How do I go? Oh, this keyboard has changed. Do you know how to undo? There it is. Okay, perfect. Okay, so V in, we wrote down that V in is VC. So this is same as V in. And so now we have, I think we have all the equations we need to solve this. Let's list the equations. So we have, let's call this 1, let's call this 2, let's call this 3. So we have 3 equations, and we can probably eliminate the unknowns. Let's try to do that. So we have P out minus V in equals I out RF, or you can write it as, right? This is the first equation. I rewrote it. I can write the third equation as V in divided by R equals, or minus V in divided by R equals I in. But then I know that I out is negative I in, so I can just use that now to get P out equals plus this is from 1, from 3, from 3 I can write V out minus V in divided by RF equals negative of I in, so V in divided by R. Let's simplify this. So V out divided by RF equals V in 1 divided by RF, 1 divided by R. And so V out divided by V in is, if you multiply both sides by RF, you get 1 plus RF divided by R. Yes, that's the expression we're after. So it's telling us 2 things. One is that V out is proportional to Vn, which is saying it's non-inverting. It's not going to be the negative. And then the second thing is that the amplification is simply 1 plus RF divided by R. So you can choose RF and R, and you'll get the amplification. Now, what is done is if you make an assumption or you choose the resistances such that RF is R is much greater. Let R be much greater than RF, which means that the ratio of RF divided by R goes to 0. Then we'll see that P out divided by V in is close to 1. Okay, which is saying that the output is the same as input. Okay, so all it does is takes the output, or it takes the input and provides it the output. And why would you use the operational amplifier in this configuration? But it turns out that an operational amplifier, because of its nature of a high impedance on the output and low impedance, high impedance the input and low impedance the output, it actually acts as like a circuit which buffers the input from the output. So it will prevent your circuit from getting your output from being damaged or things like that, because it will not allow a large current to flow because it has a very high input impedance. Okay, so in this configuration, it's basically called a buffer or a follower. A buffer or follower. Or follower. Okay, that is the output follows the input, and that's why it's called a follower. And the reason why it is used is this helps to isolate the voltage source. Okay, the voltage source is V input. Because of the high resistance, R goes to infinity. Here, R is much bigger than RF. Okay, so that's the second use. Let's look at some other uses of operational amplifier.